Hey physics peeps, we're going to take a look at this energy 4 worksheet, and there's some notes that I want you to copy down as we're going through, and then we'll solve out a problem or two at the end. So we've learned so far the total energy of a system stays the same. When objects are allowed to rise and fall down on their own, potential energy, kinetic energy are conserved. Think back to that skate park simulation we did. When the kinetic energy increases, potential energy decreases, but the total energy never changes. But when energy is transferred in a system, many times work is also done. And work is someone or something that can either add energy to a system or remove energy from a system. And that can be done in many different ways, like examples of where work is added to a system. It would be like pedaling a bike up a hill, or stepping on the gas pedal when you're driving a car, or pushing a friend on a swing. These things will may not actually, if you were trying to like pedal up a hill or drive a car up a hill, would probably not make it up on their own if you were not to give any extra push. But by stepping on the gas or pedaling, you're actually doing work and you're adding energy to the system in order for that to happen. Also, like on a swing, your friend might not be able to swing up to the top of the swing or to the highest point unless they could pump. You're adding energy to the system, or you give them a push, you're adding energy to the system. When we remove energy from the system, it could be things like applying the brakes on a car, where you slow down, or pulling a balloon that's rising in the air and pulling it down and giving it less potential energy, or friction from a machine that takes energy away in the form of heat. And so we've seen examples of that in like our labs that we've done, where our energy that we put into a machine is not always the same as the energy that we get out of the machine. And that's why. So when we end up representing that, we show work by being added or removed to a system by using an LOL diagram. The LOL diagrams really just kind of stand for the L-shaped diagrams for the graphs that we've been doing. And then the O represents the system. And we use arrows to show how energy is changing in the system. So when energy is being added to a system, what we actually do is we can draw arrows. We can say like maybe we start off with potential energy, and then later on we might have some potential energy and some kinetic energy. But if there's work added to the system, we say that work goes in. And we just show it by an arrow going into the system. When energy is removed from a system, it means that work is really going out. We just show it with an arrow. It could mean that you started off with a bunch of potential energy. At the end, maybe you ended up with less kinetic energy than what you were expecting. And there's energy that's going out of the system. So again, that little circle really represents system, or whatever you're talking about, a machine, a car. I'm talking while I'm writing at the same time. Things like that. But how we represent an equation is an important thing. So I have two equations down here, and one of these equations represents work being added to the system. And keep in mind, usually when we do these things, we're talking about things that are happening before and after. Before or after. These equations are set up where we have before and after on one side, or before on one side, after on the other side. But one of these equations represents work being added to the system. One represents work being removed from the system. I want you to pause the video and take a look at this and decide which one of these represents work being added, which one represents work being removed. All right. if you said this one is work being added at the bottom, that is correct. When we say work is being added, work is actually added into the equation on the before side. And it's because it's entering the system, that's where we write it. But when we remove energy, it's like energy, or that work can be added to the after side. We're getting some work out of the system, and that's how we can end up remembering it. So when you solve these problems out, it's important to tell where work is actually written, and it plays a key role in it. And so we're going to solve out some problems when we use work. So here's a quick example. A bicycle rider is about to go up a hill. At the bottom of the hill, the rider has kinetic energy of 250 joules. The rider does 600 joules of work while pedaling up the hill. At the top of the hill, the rider has 750 joules of potential energy. And we want to figure out, is the bicycle rider adding or removing energy from the system? And because they're pedaling, they are adding energy to the system. So they're going to be giving themselves more energy as they go. And it's not necessarily they're giving themselves, it's like them and the bicycle, that type of system. How much kinetic energy does the rider have at the top of the hill? This is where we start filling out these diagrams again. And we set up our problems with before and after. And before, that rider is at the bottom of a hill. And so they do not have potential energy. But they are moving. They have kinetic energy, they say. And so how much kinetic energy? Well, we'll just kind of say like they have kinetic energy. But they do 600 joules of work. At the top of the hill, they have 750 joules of potential energy. So this amount of potential energy is actually greater than the amount of kinetic energy than what we started with. It's like a lot greater. So it's like way up there. But it's asking how much kinetic energy do we have. Here, we don't actually know if it's zero or not. We might actually still be moving because we did work. So when we set up the problem, we did put work in to our system. And we're going to set up the problem where it's EK plus EP. But because we're adding work into the system, we could end up just writing work right here equals. On the after side, it's EK plus EP. So when we set up the problem, it's very similar to what we did before, but work needs to be put in, and you kind of tell which side that it goes on. Is it being added to the system, or is it being removed from the system afterwards? So we can cross out some energies that we didn't have, like the potential energy. We knew we didn't have any potential energy before, cross it out. But these types of energies, like we know we have potential energy afterwards, the kinetic energy we don't know. We're actually trying to figure that out. So we leave it in. And now we start putting information in where it belongs. So like here, they just tell you the energies. So we can do 250 joules of energy. Plus, they tell us how much work we do, 600 joules of work. And so we put that in place of work. Equals. And now it's our kinetic energy, which that we don't know what that is, and we're trying to solve for it. So we're going to leave it as the letter. Plus the potential energy afterwards. And that they told us was 750 joules. So here's our setup. And this is the hardest part getting to, is making sure that we actually set up the equation correctly, put work into the equation, and then actually putting in information where it belongs. We did have to include work. We did not have to include potential energy on this side because it was at the bottom of a hill, no potential energy. But now we do the math. We start combining things. So we can have 250 plus 600. We get 850 joules. Equals the kinetic energy plus 750. Oh, we can't simplify that at the moment. But to solve for the kinetic energy, to get it by itself, Now we have to undo the 750 here, and we undo it by subtracting 750 from both sides. The 750 over here goes away, and we end up with 100 joules is equal to the kinetic energy afterwards. We just solved for what we wanted, and that's what we leave it as. Sweet. And so that's a pretty easy problem, but let's take a look at one other problem, and we got some other work to do. Here, a roller coaster is tested to determine if the wheels on the track are working properly and how much friction there is in the system. The 250 kilogram train, that's the roller coaster itself, starts from rest at the top of a 12-meter tall hill. When it reaches the bottom of the hill, it reaches a speed of 13 meters per second. Is friction adding energy or to the roller coaster system or removing it? So friction, if you think of it, it's not actually making it go faster. It's making it slow down. And so it actually removes energy from the system. And when we think of this system as like before, after, doing this with our work really tells us where work is going to be in the equation. We're going to have kinetic and potential energy on both sides, but then we'll write those in. But work really goes over on this after side. And we're going to use that to figure out how much work does friction do on the roller coaster down the hill. So we're going to start this off. Before and after, we're going to list out the types of energy that we have. We say before that roller coaster is at the top of a hill. So, and it starts from rest. So there's no kinetic energy, but there's a lot of potential energy at the top of that hill. Afterwards, when it reaches the bottom of the hill, so when we say the bottom of the hill, we know we have no potential energy, but it reaches 13 meters per second. Well, if there's friction, probably going to have less kinetic energy, something like that in there. Sometimes this part is kind of vague of what this actually looks like, but we can tell that it's moving. We have kinetic energy. This lets us set up our problem, and we're going to do the similar things that we did before. We have EK plus EP, and then that's all that gets written on this side. And then on this side, we have EK plus EP. But because work is being removed from the system, we write it on the right-hand side along with our stuff because energy is going to be removed. Now we can start solving things out, but this one, and unlike the other one, does not actually give us energy. We have to figure them out. And there are some things here that we can cross out to begin with too. So like our EK from before can cross out because we don't have kinetic energy, we don't have potential energy over here. This is what we're left with. But then we need to put things in for potential energy because they don't give us energies. You can use the equations like we have been. Just make sure that when you do kinetic energy, don't forget the squared, and don't forget this work that we had put in. And we're going to solve for that. So this part, the mass, they tell us it's a 250 kilogram train. Times G, it's 9.8. Times the height, it's a 12-meter tall ramp. And then we have 1/2, or you could do 0.5, times the mass, 250, times the velocity. And here they actually tell you the velocity. It's 13, and that has to be squared plus the work. We're going to solve for the work. And to do that, we got to do some calculations. And at this point, I'm going to ask you to finish up the problem. We kind of went through setting it up. But the key thing is when we solve out a problem here and we're involving work, we identify types of energy that we have before and after. And sometimes you might have energies that you're not sure if you have, and that's okay. You keep them in if you're not sure if you have them. But then you write in work on the correct side. Are you adding energy or are you taking energy away? And if you're given energies, it makes it simple. But if you are not given energies, you do have to figure it out using the equations. You can go through and solve for what you want. Try it out. We'll talk to you later. You guys are doing great.